such an interesting subject and so puzzling that I thought you might find it interesting as an exercise to write a little essay on times arrow and put this all down, your thoughts on it, so you understand it in your own words. And you can explain to your friends. Now, we've derived the thermodynamics, and that's rather remarkable. We almost did some from Newton's equations. We derived thermodynamics of an ideal gas. But the real value of Boltzmann's equation is in treating non-equilibrium phenomena. It describes how a system approaches equilibrium, and that's called transport phenomena. Why is it called transport phenomena? Because for a system to achieve equilibrium, it has to balance things. If it has to make the density uniform, it is not. And in the process, it has to transport particle from one part of the system to another part of the system. It would have to transport energy, momentum, and particles to achieve equilibrium. In this process, these are called transport processes, and it's described by the Boltzmann equation. We have confined ourselves to neutral atoms. If the atoms are charged, you will have to bring in the electromagnetic field. Then Boltzmann's equation, in the presence of electromagnetic interaction, are the equations for so-called magnetohydrodynamics, the thing that describes plasmas. To describe transport phenomena, we have to ask, what is the agent for transport? How do things get transported from one part of the system to another? The agent of transport, of course, are collisions. And the distance over which quantities can be transported is governed by the distance an atom travels between two collisions. That's called the mean free path. Lambda is the average distance traveled by an atom between two successive collisions. So let's imagine an atom here. It moves along and it collides. And it moves along here and it collides and goes like this. That is a free path. And the average of that is the mean free path. You have to average it over all collisions in the gas. That's the mean free path. But of course, when an atom collides, there's a partner. Also gets kicked out. You know? We're just going on this one atom, but of course, there must be a partner in the collision. We would like to calculate the mean free path as a function of temperature. So what is the mean free path? Because that will tell us how far things get transported when the system approaches equilibrium. So that's the fundamental quantity in transport phenomena. So let us compute it. So let Z be the number of collisions happening in the gas per unit volume per second. And it is, you know what it is. It is equal to, first you have to find two particles, so it's F1 and F2. This is probability of finding two particles, F1 and F2. And they collide. And when they collide, you have the delta function Pf minus Pi times t fi squared, and you integrate over not only p1, p2, p1 prime, p2 prime, because this leads to the final state, and you integrate over everything, and there's a number of collisions. And this you can see we can calculate, and we're going to calculate that. I told you that we left these delta functions untouched here. You see the advantage of that. When we derived the H theorem, you can see the symmetry from that delta function very simply. But to calculate this, we have to do the integral. So it's very well to leave this undone for formal purposes, but when it comes down to results, we have to do the integral. So we're going to do that. And but each collision as you see in the picture above terminates two free paths. Therefore, the number of free paths that is number of those in between things per unit volume per second is equal to 2z. And since there are n atoms per unit volume. And therefore, the number of free paths traveled by an atom per unit volume per second is just equal to 2z over n. Suppose v is the average velocity, average speed of an atom. Then this is the distance traveled per second, right? It's a distance. It travels per second. And therefore lambda, that is the distance traveled per second divided by number of free paths per second is just equal to lambda. That's the distance between collisions. And therefore, we have the result lambda is equal to n v bar over 2z. This is the expression of the mean free path. The density times the average velocity divided by 2 times the total number of collisions per unit volume per second. Okay, so this is very fast, but we have to compute it. We want numbers. How many centimeters? We want numbers. So we compute it. We have to compute v bar, we have to compute z. V bar is the average velocity, average speed. So the speed distribution, I can just use here, the speed distribution it's not f, but it's 4 pi p squared times f0 p. Because the speed it has no direction, so you multiply by 4 pi p squared. And you have to, if you plot this against function p, this is after p, and this is thing, you get something like this. And this is v bar. This is m times v bar. So we can define the average velocity as the maximum of the peak, the most probable. Now, since the thing is Gaussian, this is very easy, right? You have I have p squared, never mind the 4 pi, p squared f0 p. I want the maximum, so ddp is equal to 0. So I have ddp times p squared. The c doesn't matter, so it's e to the minus alpha p squared is equal to 0. And so this gives me 2p times this minus 2 alpha p cubed times e to the minus alpha p squared is equal to 0. So the average speed is given by the 0 of this. And so p bar is equal to alpha p cubed. And you can cancel it, and therefore p bar is equal to 1 over square root of alpha, and therefore v bar is p bar over m, which is equal to 1 over m alpha, and v bar therefore is equal to, put in alpha, is equal to 2 kt over m. Now, if you put in some numbers under standard conditions, this is rather a large number. I think it's something like I forgot, 10 to the 5th centimeters per second, something like that. So in that little cube, I'm just going like mad, like crazy. That's the average velocity. So now we have this. Now we have to compute z. And z is given by this expression. So let us compute that expression. Oh, but before we do that, I would like to do some of those integrals involving the delta function and try to express that in terms of the scattering cross-section. So to we do that, we have to define the scattering cross-section, which one uses in experiments in collisions. So first I have to define scattering cross-section. You have a target here, a target atom. It's an incident atom. It comes in with P1. This is the incident atom. This is a target. Actually, we have to think of it as a quantum mechanical process. This is what's coming as a plane wave. It's a stream of particles coming in as a plane wave. And then after scattering, this particle goes out in a certain direction. And this is P1 prime. And this thing recoils to P2 prime. Here P2 was 0 to begin with in the lab. This is the recoil. And this is scattered particle. This is recoil particle. Now, we want to measure this. So we put a detector here and catch this. Since P1 prime lies in the continuum, you have to define a little volume element in that space. So what you do is you you consider all the momentum come out in a solid angle, d omega. You put a detector and you count how many particles enters that solid angle. And this angle is theta, the scattering angle. And the angle around here is phi, is the azimuthal angle. Sometimes it kind of depends on phi, sometimes it does not. And P1 prime and P2 prime, so they're constrained by the conservation of energy conservation, right? So energy conservation says that epsilon 1 prime plus epsilon 2 prime is equal to epsilon 1 plus epsilon 2, where epsilon is p squared over 2m. And the momentum conservation says that p1 prime plus p2 prime is equal to p1 plus p2, and this is in the vector sense. The incident beam has a certain intensity. There's a beam coming in like this, and it's characterized by an incident flux. It's a number of atoms crossing unit area per second. But if you hold down a wall here, you count the number of atoms coming here per unit area per second. Per unit area per second. And that's called the incident flux. It's I. For a density of 1 atom per cc, 1 atom per unit volume, I is just equal to V1 minus V2. The velocity of approach of these two particles, V1 is V is equal to P over M. So this I is just the relative velocity of approach of the two partners. So they call it the I d sigma. D sigma is the element of scattering cross section. It's defined as a number of atoms scattered into d omega per second divided by the number of incident atoms per unit area per second. No, I'm sorry. It's just equal to this. And therefore, d sigma is equal to this above divided by I. And when you look at what this means, d sigma is an area. This is an area. That's why it's called a cross section. It's called a differential cross section. What area is this? Well, and you have these particles scattered into this solid angle d omega. So many scattered per second. Now you ask how many particles scattered into this omega? It's d sigma. And what is d sigma? D sigma is equal to the area cut out in the incident beam. Sigma, this is d sigma. If you cut this out, all this particle will scatter into here. And so that is why it's called a scattering cross-section. So it's differential cross-section. And this is the quantity you measure in the laboratory. And when we do the integral, we will try to maneuver the integral so that this appears in the integration so we can use experiments. And d sigma, d omega is the differential cross-section. It's the area per unit solid angle. And you integrate this over all solid angles. Over 4 pi. This is called a total cross-section. Usually the total cross-section has a geometrical meaning. Right? It is, if you scatter off of an obstacle, this cross-section is of the order of the area of that obstacle. Because the incident particle that hits that obstacle gets scattered. So that's an intuitive way to understand this. But quantum mechanics, that's only a rough idea. When you calculate quantum mechanics, it's not always true. Sometimes it's off by a factor of 2. Because in quantum mechanics, what's being calculated are really waves, not billiard balls. But this is the general definition. Now, how do we relate this to our TIF? So we're going to do this integral. This seems like a very long introduction in order to just compute this integral. But I think a knowledge of that is useful in general because the scattering process is a very common one in physics. And these definitions are standard. So, in terms of TIF, etc., I d sigma is given by the probability, the differential probability of 1, 2, 1 prime, 2 prime. This, I think I've used this notation before. The probability that is the rate at which this process goes on. And you integrate over P2 prime and P1 prime, but only the magnitude, because you want to leave the d omega free. Times d omega 1 prime. And so this is going to, I'll just write d omega integral d1 prime squared d1 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 prime, d1 prime, and d1 prime squared, integral over d3 p2 prime, integral over everything in the final state times dp1 2 1 prime 2 prime. And the differential cross-section, V1 minus V2, that's I, times d omega by d, is just equal to integral over P1 prime magnitude, P2 prime, the whole vector times dp 1, 2, 1 prime, 2 prime. And now in our discussion last time, we have an expression for this in terms of the transition matrix, right? You recall what it is? I'll just write it down. This is equal to integral p1 prime magnitude p2 prime all vector. This dp is just equal to the delta function of df minus di t fi squared. And so now, if you recognize this integration in our computation for z, you can substitute it for differential cross-section. So now let us write down, let us go back to our expression for z, which I wrote down earlier. It is just the integral of this. It involves the integration of this over everything. Because we need to get z, we need to do the integral delta 4 p final minus p initial t matrix squared integral over p1 prime p2 prime. And of course, this is equal to p1 prime can be decomposed to d omega p1 prime magnitude times p2 prime thing, and then delta 4th times t squared. This is therefore v1 minus v2 times the differential cross-section. And since I'm having a d omega here, this is just equal to v1 minus v2, the initial flux, times the total cross-section. So this thing very nicely collapses to something very simple. In order the total cross-section of the scattering, and you can either compute that or you can take it from the experiments. And all of the work is just for the step that we want to calculate the total number of collisions per volume, per unit volume, per second. And from the expression that we derived earlier, it is given by z is equal to integral p1 p2, which is v1 minus v2 times total cross-section times f1 times f2. And that's very simple, especially if you assume that the total cross-section is independent of momentum, which is not exactly true, but it's a good approximation. So let's assume sigma total is a constant. Then I can do the integral. Then z is equal to sigma total divided by m because I want to convert that into so p1 minus p2 sigma total f of p1 f of p2 d3 p1 d3 p2, and that's an integral you can certainly do. The easiest way to do this let me just write down one step. This is equal to sigma total over m times c squared times integral d1, d3, p1, d3, p2, p1 minus p2 times e to the minus alpha p1 squared plus p2 squared. And these are vectors, vector squared. Now this factors into that, but this doesn't factor. So the way to do this is to go into center mass coordinates. You introduce center mass coordinates. These are in the lab frame, so to speak. You go to the center of mass coordinate system. Center of frame. You need to find P as P1 plus P2. Small p as 1/2 P1 minus P2. And then you will find that D1, D2 is equal to D3P, D3 little p, and that P1 squared plus P2 squared is equal to P squared divided by 4 plus 2 times P squared. And then with this, the integral just becomes total cross section equal to m c squared integral d3p e to the minus alpha p squared over 4 integral d3 small p times the magnitude of p, that's what this is, or twice that, 2p times that, times e to the minus alpha 2 alpha over p. This is a Gaussian integral. This is an exponential integral. You can certainly do that. They're all elementary. So I'll just give you the answer. The second is a exponential integral because the 2p is a derivative of the exponent. So it's not even Gaussian. It's just exponential. And the answer is z is equal to (2 over root pi) times the density squared times the total cross section times the average velocity. And so the mean free path is therefore equal to pi over 8 times 1 over n times the total cross section. This pi over 8 is not important. The important difference is 1 over the density times the total cross section. And notice this is independent of the temperature. And it's proportional to n sigma total over. And you can also define this as a mean free path. It's inversely proportional to the density, which makes sense, right? The denser the particle, the smaller the mean free path. You can divide a mean free time. Which is the average time between collisions, tau. This is just equal to lambda divided by v bar, which then is equal to pi over 8 into the square root times 1 over v bar n times sigma total. This one does depend on the temperature because v bar does. So for an estimate, take sigma total equal to pi a squared, where a is of the order of atomic diameter. A is of the order of atomic diameter. For example, for H2, we can take A to be 1 angstrom, 10 minus 8 centimeter. And then if you plug it in, you will find that lambda under STP, standard temperature and pressure, lambda is 10 to the minus 7 centimeter. And tau is 10 to the minus 11 second. So you see the order of magnitude. The meter is very tiny. The atom doesn't go very far before it collides. 10 to the minus 7 centimeter under standard conditions. And the time between collision is very short, 10 to the minus 11 seconds. So in 1 second, it makes 10 to the 10th collisions. That's why this gas can approach equilibrium very fast. It thermalizes very fast because of this. And you ask, where did these come from? Where did these rates come from? It comes from atomic diameters, 1 angstrom. And where does that 1 angstrom come from? It comes from the Bohr radius. And where does this Bohr radius come from? It comes from electromagnetic interactions, because the atom is bound by electromagnetic interactions. And the Bohr radius is of the angstrom. If you have astrophysical processes in which the cross-section is much smaller, say neutrinos, then mean flight is much longer. A neutrino has a mean flight of longer than much the size of the solar system. Maybe you can go through anything before it collides. A neutrino doesn't collide, essentially. That's why it's very hard to detect neutrino collisions. You have to detect so many trillions before you see 1 collision. So all this depends on the interactions, right? Somebody said that somebody once made a calculation. Said that for a neutrino, the chances that you get hit by a neutrino in your body is once in a lifetime. The muscle usually change, the sun is really raining on you, but most of them don't collide. But once in your life, you get hit once, and that's the one that kills you. But we're talking about electromagnetic interactions, and the typical time scale is 10 to the minus 11 seconds and 10 to the minus 7 centimeters. Very, very strong. Now we know the mean free path, which is the agent, which is the typical dimension over which quantities get transported. So when we talk about transport processes, there are 2 limiting cases that we can consider. Two limiting regimes. One is called the collisionless regime. In which lambda is much greater than L, where L is a relevant dimension in the problem. For example, if you have a high vacuum, then you would want very few atoms inside. So in high vacuum, people work very hard to pump this out, right? So there are very few gas molecules inside. So the collisions happen very infrequently. So when you have an atom here, it would bounce off the wall, so it would make a lot of bounces before it makes a collision. So here, the mean free path, if this is L, the emitter is much bigger than L. That's a collisionless regime. Such a gas is called a Knudsen gas. It's very important because people were experimentalists, always have vacuum systems. And it's very important to understand your vacuum system. And in a vacuum system, you had better have the collisionless regime, right? So you're in the regime in which the mean free path is very large, much larger than the size of the box. Another manifestation of this regime is when a gas flows through a hole. The hole is small relative to the mean free path. So let me illustrate. Here's a wall in the gas. And this is D. And the mean free path is much bigger than D, than L. What does this mean? That means that if a gas goes through this hole, the last scattering happens on the other side. So this goes through this hole without scattering. And that's a collisionless regime. And when the gas goes through such a hole, this process is called effusion. It doesn't flow through, they just go through. And the last scattering is on the other side. And we can compute the rate of effusion very simply. The number of atoms crossing this hole per unit area per second is called a flux. Flux I is equal to the number of atoms crossing the hole per unit area of the hole per second. And we can compute this because di, an element of this flux, is just equal to the number of particles with a certain Vx times d3p. d3p times this is a density, and Vx is the flux, is the velocity with which it goes through the hole. Right? And so I is the integral of this. dTp, Vx, f of p, f0 is Maxwell-Boltzmann, p. And of course, you have to integrate over on a v greater than 0. Now, this integral, by now, you know how to do this integral. This is a Gaussian. This is linear. So you can do this. I'll give you the answer. The answer is n, the density, times kt over m into the square root. This is the rate of the flux of effusion. So if you have very dilute gas inside a tank, then when it comes out of this hole, the rate is inversely proportional to the square root of the mass of the atoms. That means that if the atom is heavier, it comes out more slowly. So you can separate isotopes. In fact, this is how you separate U-235 from U-238. When they construct the first bomb, this is what they use to separate the isotope. They make it into gas, and they let it diffuse through these holes. They have a series of them, so big that it covers acres. Keep diffusing out. So the first time the ratio of 235 and 238 increases a little bit, you get it. You do it 100 times, you get enough, or maybe 1,000 times. So that's effusion. That's what you use for separating isotopes because of the mass dependence. So you see that it's not obvious when they ask you how's the rate of diffusion. When you compute it, you find 1 over squared of m. Then you say, I can use this. The other side of the coin, the second process, is the other extreme in which the mean drift path is very small. So the second regime is called the hydrodynamic regime. And this is very important because it's much more common. And this lambda is much smaller than L. You can appreciate this if I just draw a picture. If I do the same thing again, the gas going through the hole. The same hole. It's L. But now the mean path is very tiny compared to the L. How would the atoms go through? They would do this, right? They make a lot of collisions. So they make a lot of collisions. Maybe they come back and they come out like this. It doesn't come out clean like this. It's a collective flow. So you get the average flow. And that's the hydrodynamic flow. And we can compute that. We can calculate that because we have Boltzmann's equation. And therefore, the next topic is to derive hydrodynamics from Boltzmann's equation. In between will be very hard. In between, you'll have to solve Boltzmann's equation. Now, that's very simple, right? This is also very simple in principle. In principle, we just assume that the gas is in local equilibrium. That is, the derivative is C F C times e to the minus alpha p squared. But now you have momentum. It moves, something like this, in which C, alpha, and p are all functions of the temperature and density. These are all functions of the density and the temperature. That when you go from place to place, it varies very slowly. So that locally it looks like it's equilibrium, but with a fixed temperature, but the temperature changes slowly. And so is this P. And thus the P is a streamline. You should have hydrodynamic streamline. And our object is to derive equations for these average quantities. And those are called the hydrodynamic equations. Once you have those, you have the most useful equation is the Navier-Stokes equation, which you use to predict the weather. And we'll derive that next time.